Mike Dudley here from the Virginia Asphalt Association to talk to you about testing asphalt mixtures. This is Chapter 6 in the Asphalt Plant Level 2 class, and we're going to focus on the first portion here on the asphalt content and gradation. One thing I do want to point out to you that Chapter 6 will be broken up into multiple presentations. The reason we are breaking it out into so many presentations is so we can cover these test procedures in a lot more detail and give you a lot more information. Little overview. Through many years of laboratory testing and road applications and basically experience, VDOT has established design ranges on the SuperPave mix design system for all asphalt mixtures in Virginia. Basically what happens is when an asphalt sample is tested in Virginia, we can analyze the data and determine its probability of performance and conformance to the VDOT specifications. Some of the tests we run are the asphalt content, which is measured through a furnace burn, a gradation analysis that we'll do, that'll be focused on in this presentation. In additional presentations, you're going to hear about specific gravities, both the theoretical maximum specific gravity, or RICE. The reason it's called the RICE test is because a gentleman with the last name Rice invented it, by the way. Also, there's a bulk test where we measure the voids, bulk specific gravity test, and we measure the voids of our specimens. You'll also hear in other presentations some talks about volumetrics, about how we measure moisture in the mix. And we're going to also talking about a stripping test, which is the tensile strength ratio test, TSR test, or the Boyle test. Both of them are stripping tests. Here's a table you can find in Section 211 of the Road and Bridge Specifications. I won't go into detail and read this to you, but basically it gives you the design parameters and production parameters for our mixes, whether it be volumetrics, VTM, VFA, VMA, different ranges based on different mix types. You got an SM 4.75, which is our finest mix, all the way down to the BM 25, which is our base mix. So all these parameters can be found on this table, which is also found in Section 211 of the Road and Bridge Specifications. So our learning objectives for this presentation is to talk about how you determine the asphalt content of a mixture with the ignition furnace. And the specification we use to do this test is VTM, Virginia Test Method 102. We'll go through that in detail. Once we've established the asphalt content, we'll then talk about how we determine the gradation of the sample, which for this test procedure we follow AASHTO T30. One thing I do want to point out for acceptance testing, when a plant produces a mixture, it must be tested to ensure the mix meets VDOT specifications. So basically the asphalt content, the gradation that the contractor does the testing on is what is used to determine payment for this particular mix. When VDOT does the same corresponding test, their data is used to correlate that the contractor's data is reasonable and looks correct. But payment is based on the contractor's test results. Start with Virginia Test Method 102. It utilizes the ignition furnace for burning off the asphalt binder from a mixture sample, and it leaves behind an aggregate blend. This aggregate blend can then be cooled off, and we're able to actually run a gradation and see how that correlates to the specification requirements for this job mix formula. Always want to talk about safety first. You see here in some pictures, you see a face shield, you see some gloves, you see some long sleeves. These furnaces, for them to burn the binder right off the aggregate and off this sample, they're currently running at 1,000 degrees Fahrenheit. So this isn't just a normal oven like you'd have in your kitchen at home. You need to make sure you're protected when you're opening and closing these doors. Also, you'll see here this red basket. I'll talk more about that, but when that sample comes out, it comes out at 1,000 degrees Fahrenheit. We want to make sure we have a way of covering it in case somebody else walks by, they don't touch this sample at this extreme temperature. The equipment that we need, the first picture you see here on the left is your in-cap furnace, which is the typical furnace used in the state of Virginia that does the actual test. You can see the baskets. This is how we spread our sample out to make sure the samples burn well. Top right is a balance or a scale that we need to get our weight, because we have to have the weight of our sample. You also see a large pan here shown with some brushes and spatulas and that we use to clean out the baskets. Also, you see an oven here. The reason there's an oven here is our sample has to be pliable when we put it in the basket, so it has to be warm enough that we can maneuver the sample when we put it in the basket. To obtain our ignition sample, we take a representative sample from the center of the truck according to VTM 48, done been covered in the Plant 1 class, and then you quarter it down, also covered in the previous class, according to AASHTO R47. One thing I do want to note here, that if your sample mixture is not soft, if you've allowed it to cool down, or you had to drive from your plant back to a central testing laboratory or something and your sample's cooled off, and you need to heat it up to make it pliable so you can do this quartering method and you can add it to your baskets, you are to heat it in an oven at 257 plus or minus 9 degrees Fahrenheit for 25 minutes. But that should get it pliable. The one thing you can't do is heat it more than 1 hour, or you may actually begin to lose some of the asphalt binder that would be part of your sample. So it's important to see that time and temperature range there for reheating ignition samples. When it comes to sample size, this table can be found in VTM 102. What you have here is a table based on your nominal maximum aggregate size, going from a 4.75 millimeter down to a 37.5 millimeter, a very large aggregate base mix. And notice, depending on the sample size, depending on a gradation size, you have different sample sizes that are required. For our smaller samples, like our 4.75 and our 9.5 millimeter mixes, our surface mixes, we can have samples down to a minimum 1,200 grams. As we get larger, the minimum base sample, a typical BM25, is going to be 3,000 grams for the minimum sample. There's also a maximum weight that we can have, and that would be a maximum of 500 grams more than the minimum sample weight. So if we're looking at this SM 9.5 sample here, it says we have a minimum sample weight of 1,200 grams. The maximum sample weight would then be 1,700 grams. So our representative sample has to be within that range in order to do our testing. When we're weighing the sample, the first thing we got to do is we're going to weigh the sample right in the baskets. Okay? To do that, you can see an image here of how we're loading our baskets, and you can see he's keeping the sample away from the edges. Once we've put our sample in our basket, we've noted two different weights. We want to weight our individual sample weight, and we also want to know the weight of our sample and basket combined. Both of those need to be written down. The reason they need to be written down is right now, I need to enter the sample weight into the furnace. That's what you can see the technician doing here. He's entering his sample weight, and at the same time, every mix previously during this mix design phase would have established a correction factor. It's called a furnace correction factor for each mix. The technician also needs to enter that correction factor that's specific for this mix before he runs his test. When he's loading his sample into the oven and to the furnace here, this is the ignition furnace, he wants to make sure the baskets are not touching the back or sides. The sample, while it's loaded into this furnace, is actually suspended over a scale in the bottom portion of this furnace. So it's very important that these baskets not be rubbing any back, front, or sides of the oven, so it can properly note the amount of weight loss and calculate the correct asphalt content. Once this test is complete, the technician will remove the sample from the furnace, and as we noted earlier, because this sample is at 1,000 degrees Fahrenheit when it comes out, he's going to place it under a basket or under some protective cover until it's cooled off enough that he can then work with it. And here we have a video that's showing you these steps. All right, here the technician is getting his sample weight, 1,654 grams. From this, That's to give him a reference. He's now going to load the sample in his baskets. He first removes the top, and then he's going to remove the upper basket, set it to the side, and he's going to place half of his sample in the lower basket. There's no exact weight here. He's just referencing by eye approximately half of the sample for the lower basket. Now he spreads this out nice and uniform because you want it to be as thin as possible so that you get a good complete burn. Notice that none of his material is around the edges. He's pulled everything about a ½ inch into the middle of the basket, away from the edges, a ½ inch away from the edges. That's because the way the furnace works based on weight loss, if anything fell through one of these holes, an aggregate would fall through the holes, it would be perceived as weight loss, which would be binder. So it's important that both these baskets have the material pulled away from the outside edges. Technician now is spreading out the second portion of the sample, making sure it's nice and uniform as well. As you can see again, not touching the outside edges. Now the technician is putting the top back on his basket, and he's going to note this weight, 1652.6. He's also going to note the combined weight, 4,896 grams. Here he is, the technician's entering his sample weight into the furnace. He is unable to enter a decimal place, so he's entering 1653 for the weight, as you can see there in the center. Next, he's going to enter the furnace correction factor that he would receive from his mix design technician. The correction factor for this mix is 0.40. You can also see that noted there. Now the technician is going to load the sample into the furnace itself. Making sure it's not touching the back or the sides. And notice he's now checking to make sure his combined weight is fairly close to the weight the furnace is showing prior to hitting start. Once he starts the test, it will burn till it's complete. The furnace shuts off automatically. You can see the word done there. That means that the furnace has completed the furnace burn. And now the technician will hit the start-stop button, which unlocks the furnace door for safety reasons, so he can now remove his sample. Here the technician is carefully removing the hot sample, placing it on a platform to cool, and covering it for safety measures. It's obvious now that it's cooled off enough that the technician can touch it. What he needs to do now is he needs to remove the aggregate in order to do his gradation. Here you can see a picture of the burned sample. You can see how well and uniform, there's no asphalt binder left on this sample. All right, so what is a gradation? Gradation is determined by passing material through a series of sieves stacked with progressively smaller opening from top to bottom. Basically, we're going to separate it based on different squares, openings that got smaller as we go down. Once you've done your sieve analysis, it's had time to properly disperse throughout the sieves, you're going to weigh the particles retained on each sieve and note these weights on each sieve. Here's just a sample gradation to show you what it would look like a couple different ways. One is a numerical gradation that shows you the percent retained, the percent passing. The other image here is a graphical presentation that will show you the actual graph of how it's on a 45 power plot showing you the actual same gradation. So to obtain the gradation sample, once it's cooled to room temperature, as we noted above, you got to remove your sample from the baskets. And here you hit the technician, and you can see an image of where he's gone through the process of removing the sample. Once the sample's been removed, it's important that we wash the sample over a nest of sieves. This nest of sieves is basically two sieves, with the bottom sieve being a number 200 sieve, and the sieve above that is a number 16 sieve. The purpose of this number 16 sieve is to protect the much finer, much easier to damage the number 200 sieve than it is the coarse wire that you'll find in a number 16 sieve. So the purpose of the 16 sieve is solely to protect the number 200, because the whole sample is being washed over the number 200 sieve. When you're washing a sample, it's important we add a wetting agent. That's to make sure that all the real fine material that's coating the larger aggregate is dispersed properly and allowed to pass through this number 200 sieve. And one thing to note, a lot of us use these mechanical washers. There is a maximum amount of time allowed for these mechanical washers, which is 10 minutes. Now here's a video of the actual washing sample. We'll go through this. Here the technician is showing you he's got a couple different brushes to clean out the furnace baskets. He's got a really large pan, big enough to hold the whole sample and not lose any of the material. He's just going to dump it out. One thing I do like about this particular setup is the technician has a fan in front of him pulling any of the dust material that may become airborne away from him. Now you can see he's got a wire brush on this material. He's taking his time to clean it out with a very stiff wire brush, making sure he's getting it all cleaned out, his entire gradation sample. You can see he's putting quite a bit of force on this as he's cleaning these baskets out. He'll do the same for the second basket. And then he'll clean out the pan, because the material there is also part of the gradation. So he just uses the paintbrush, which is a hair bristle type brush versus the wire brush, to make sure he's got everything cleaned out. Once he's done this, now he's got his gradation representative sample. He wants to weigh it. So he's going to transfer it to a different pan to get the total weight. Here he is, he's teared his pan off. Now he's going to be very careful. He's using again a brush to make sure all his sample ends up in this bowl so he gets an accurate weight. Looks like his sample weight's 1,555.2 grams. That would be his weight before washing. For this video, you can see the technician is actually going to hand wash his sample. Either process is permitted, whether it be by hand or by mechanical washing. There he is adding a drop of a wetting agent. Basically any kind of soap you got, it's your wetting agent. Okay, and notice how dirty the water is here. And he's going to decant or pour the water through the same nest of sieves, which is a number 16 sieve, and below that is a number 200 sieve. So he'll continue to do this several times, 6, 8, 10 times, until the water gets clear. Again, pouring off the excess water. Once the water's clear, he's going to clean his sample back into the bowl. Here he's just rinsing off that extra coarser material right back into his sample bowl. That's all he's doing here. And then he's going to do the same with what's retained on the number 200, which was the lower sieve in his nest. First, he's going to rinse it down to one side of the sieve so he doesn't have a whole lot of water to have to dry off before he can do his gradation. Now he's got his sample all in this one bowl. He's going to transfer it to a larger pan. The sole purpose here is so that this sample can dry faster in a spread out thin layer, more so than in a large round mass. There it is, spread out nicely. And he's going to place it in the oven to dry. All right, once this sample's dried, he's ready to do a sieve analysis. Basically, a sieve analysis is what happens when you separate your gradation sample into individual sizes using proper sieves. What you see pictured here is a Gilson sieve shaker with a nest of 12-inch sieves in it. And we've talked about earlier, the top sieve here could be a 3/4 inch with a 200 at the bottom and a pan on the very bottom. One thing you need to note here also is this is one particular kind of sieve shaker. There are multiple kinds of shakers on the market, and also that AASHTO T30 does require that we calibrate proper sieve time. It is a requirement that it be done annually, that you need to check your sieve time. And the way you do that is you basically put your sample, when you do one of your gradations, you then handshake each sieve for an additional 60 seconds to make sure you had adequate sieve time, that the entire sample was properly sieved down. But all that's explained in the AASHTO T30 test procedure. Here the technician is cleaning out each sieve. As he cleans out each sieve, he's writing the weight down that was retained on each sieve. The second image here happens to be the difference you can see in a 12-inch diameter sieve and an 8-inch diameter sieve. Wanted to point out that typically used to be, before SuperPave, we used Marshall specimens. We worked with smaller samples. These smaller samples then were regularly tested on 8-inch sieves, and I still see a lot of 8-inch sieves used throughout the industry. Those are now classified as a soils sieve, and the larger diameter 12-inch sieves are classified as aggregate sieves. And you'll see more throughout this presentation of the importance of having a large enough sieve to do proper representation. Here the technician has done this. He's already shaken his sieve for approximately 10 minutes. He is using 8-inch sieves here, so he's cleaning out each sieve and writing the weight down. Notice this is the number 4 sieve, how much material was retained on that number 4 sieve for an 8-inch diameter. We have to be careful not to overload these sieves. Here he is continuing to clean out these sieves. Notice his brushes change based on the sieve he's actually cleaning it out. The finer material will get a hair brush, as you see here. This is a 200 sieve, it looks like. And he's cleaning it out with a finer bristle brush that won't damage the sieve. And he's also got to clean out his pan material, add it to the sample. Once the technician has written down all his weights, we basically have an example of a sieve analysis here. You can tell based on this sample the amount of material retained. There's nothing on the 1/2 inch, very little on the 3/8, quite a bit on the number 4. That would tell me that this is probably an SM 9.5 mixture sample that he ran. You can also tell, one thing I'd like to point out here is, notice on the number 4, there was 507 grams of material retained on that number 4 sieve. That's a lot of material. According to the AASHTO specification, the maximum amount of material that can be retained on an 8-inch diameter sieve is 330 grams. So for this particular sample, the technician would have either needed to have done this gradation on a 12-inch diameter sieve, or he could use 8-inch diameter sieves, but he would then have to split his sample in half, do it as 2 separate gradations, then recombine mathematically before he does his calculation, so he doesn't overload this number 4 sieve. The other thing I want to point out to you, it's important to note that you did a proper cleaning of your sieves. In order to do that, you want to compare sum of your weight from each sieve, in this case 1391.8, to your weight after washing that we wrote down, which was also, again, 1398.1. So this technician did a really great job of cleaning out his sieves. Here are the formulas. Go through them real quick to calculate your sieve analysis. First, you want to calculate your percent retained. That's simply the weight retained on each sieve divided by the dry weight before washing. You'll see an example of that in just a second. We multiply it by 100 to convert it to a percentage. Once we've got a percent retained, we then subtract that from the percent passing the sieve larger to get the total percent passing. You'll see examples of both of these as we go forward. Here's the same sample gradation with the formula for percent retained. All right, note that there was no weight retained on the 1/2 inch sieve. So guess what? That means there's 0% retained on the 1/2 inch sieve. So we do have 52.5 grams retained on the 3/8. To calculate that, we take the 52.5, we're going to divide that by the sample weight before washing. Okay, that was the original dry sample weight, which was 1485.3. Once we've done that division, we multiply it by 100 to convert it to a percentage, and that tells me I got 3.5% retained on the 3-inch sieve. We were talking that there was a lot of weight retained on the number 4 sieve. As you can see from here, 507.6 grams retained on the number 4 sieve. We're going to divide that by the weight before washing, 1485.3, and then times 100 tells me that I've got 34.2% of my total gradation sample weight retained on that number 4 sieve. That shows the importance of using the 12-inch larger diameter sieves to make sure we get accurate representation of our gradation. And the same formula will be used as we go through this process. Just see how it steps out. With a total of 2.6% retained on the number 200 sieve. Once we've done our percent retained, we're going to move on and calculate our percent passing. For the total percent passing, if nothing was retained on the 1/2-inch sieve, that means 100% of the sample passed the 1/2-inch sieve, so we got 100% passing. Using that 100 to calculate how much is passing the 3/8 sieve, we simply take the 100 from the sieve above minus the 3.5% retained, tells me I got 96.5% passing the 3/8 sieve. Number 4, again, if I'm using a calculator, I got that 96.5 still in my calculator. All I do is subtract the 34.2, which will give me 62.3% passing the number 4 sieve. Follow this process throughout the entire gradation. And our minus 200 will end up at 6.3% passing the minus 200. So what do we do with this information? What do we use this for? We just went through how you obtain an asphalt content through a furnace burn, and then what we do and how we get a gradation. We execute the gradation, how we calculate the gradation. Well, basically, as we mentioned earlier in this presentation, payment is based on these numbers. So the first thing we want to do is once we've completed these tests, we want to make sure it goes into mits and plaid, and then we want to correlate that our specimen, our mix, is meeting the specification requirements. There was ranges, as we saw, that will tell us whether or not we're within those specification requirements or not. As long as we're within specification requirements, we're good. One thing I always like to point out is your control charts. It's easy to look at numbers and see how they go, but a real nice visual, at least for people like myself who are visual individuals, I would look at the control charts and see how the plots are going. I don't want a lot of bouncing up and down with these control charts. I want them to stay fairly consistent. If I have a lot of bouncing, there's also a penalty that can be attained through standard deviation. So it's another good resource that we want to use as we're going through this. But remember, our asphalt content and our gradation from the contractor is what we use for payment, and it's important to check each one of these regularly. With that, if you have any questions, you can reach out to your proctor, or also want to mention there's some knowledge check questions at the end of this chapter. Thank you.